Hi, this is your video notes for section 4.1, which is about something that's called implicit, that's not right, implicit differentiation. And it shouldn't take too long to do these because you really already know how to do this. Differentiate, don't talk and try to spell things at the same time, kids. Differentiation. Implicit differentiation. You already know how to do this. It's really like related rates, except I think even a little bit easier. So let's say you have a situation. We're going to jump right in with an example here. How would you take the derivative of something like this? Let's say the sine of y is equal to x squared plus y. Now, a couple objections here. First of all, whether or not this is a function, it may or may not be, but try as hard as you want to. You would not be able to solve this for y. You can't somehow isolate and using rules of algebra isolate the y and get it into y equals form. So we don't have our regular sort of dy dx equals and then stuff with only x's on the other side. So we have to find a different way to deal with this if we want to be able to talk about the derivative of this. And this is what we do. We do it very much like we're still taking a derivative. It's not like related rates. We're not talking about time. It's not a hidden variable here like in section 3.7, like those related rates problems. But we are going to proceed very much in a similar way. So I'm just going to go ahead and start taking derivatives, and we'll see what happens here. So what's the derivative of sine y? It's cosine y. But y wasn't the derivative. Y wasn't the variable of choice here. X is the variable of choice. So every time you hit a y here, just like very similar to related rates, a dy dx is going to pop out. Just like a dy dt would have popped out in related rates problems. But notice that it's dy dx, not dy dt. What's the derivative of x squared? Well, it's 2x. And x is the right variable, so nothing pops out here. You could, if you want to, you could think like a dx dx pops out, but of course dx dx would just be 1, right? And then what's the derivative of y? It's 1 dy dx. Okay, what do we do with that? Now you solve for dy dx. Solve for dy dx. So let's see. That means I want to get all the terms with a dy dx in them on one side. Oops, sorry. So I move this one over to there, minus dy dx. That's a messy looking minus sign there, equals 2x, and then I factor dy dx. It's similar math, similar algebra to what we often do when we're finding the inverse of a function. Might feel kind of familiar that way. Right, so there we go. We found the derivative. Now, a word about what this is called. This is called implicit differentiation. That means that when you find your derivative dy dx, it's defined implicitly in terms of x and y. Whenever possible, we would definitely prefer to have dy dx equals and then only x is over here on this side. We would definitely, absolutely prefer that. But if we can't, then, I mean, this is certainly better than nothing, right? But notice here, you'd have to have the x and the y. And that's often true because in these kinds of situations, often we don't have a function. So knowing the x-coordinate by itself is not enough. We need the x-coordinate and whichever one of the y-coordinates, because we're talking about things that fail the vertical line test, right? Points are stacked up on top of each other. So we need both coordinates to find that slope. All right? I'll do a couple more examples. You might wonder, well, hey, that means I can take the derivative of something like the unit circle. So there's the equation for the unit circle, and I take the derivative of that. It'd be 2x plus 2y. Every time I take the derivative of a y, a dy dx pops out, equals 0. Of course, That's an easy mistake. Sometimes people leave those constants hanging around. And then after a little algebra, dy dx, the 2's cancel out. So I get minus x over y. Right? And then we could use this to find the equation of the tangent line to the unit circle and you could pick any point you want on the unit circle. How about the point 1/2 comma square root of 3 over 2, right? We know that's a point on the unit circle. So let's see. There's my point, so I just have to find the slope. So dy dx here, it's negative x over y. The 2's cancel out there, so that's negative 1 over the square root of 3. If that offends you, you could write it as negative square root of 3 over 3, but we don't really care about that anymore. And so the tangent line would be y equals the square root of 3 over 2, minus 1 over the square root of 3 times x minus 1/2. All right, notice I moved the minus y over to here. I like that better. So there's your tangent line. Right? One more quick example. Let's take another curve where we cannot solve for y. Like, for example, how about xy squared plus 3x squared minus x squared y equals 5. Whatever that might look like. And you can play around if you want with the algebra, but you cannot solve that for y. All right, so let's see. Let's take the derivative. Got some product rules going on here. So the derivative of x times y squared, that's the derivative of the first, which is 1, times the second. Nothing pops out because I didn't take the derivative of the y. Plus the first times the derivative of the second. Every time you take the derivative of a y, a dy dx pops out. Plus derivative of 3x squared is just 6x. Minus, be careful here, it's minus that product, so I'm going to put that in a big set of parentheses. The derivative of the first times the second plus the first times the derivative of the second equals, 0. Okay, now let's clean this up and try to solve for dy dx. Let's see, so I'd have 2xy dy dx minus x squared dy dx equals, and then I'm going to move the other terms to the other side, move that over, so that's 2xy minus 6x minus y squared. Then I'll factor out the dy dx. I'm skipping a little bit of algebra here, and then dividing by what's left behind there. Right? Can you cancel those out? No, absolutely not. Cannot cancel over addition and subtraction. Okay, now I'm going to figure out where this is a little bit of a tricky question now, but you will see questions like this for sure. So, where does this curve, whatever it is, have horizontal tangents? Well, let's see. If we're going to have a horizontal tangent line, the derivative has to be equal to 0. dy dx must be equal to 0. And that means the only way a fraction can be equal to 0 is if the top is 0, right? That means that 2xy minus 6x minus y squared must be equal to 0. Right? Think about that for a minute. And, well, that doesn't really tell me much. That just gives me a condition, like a relationship between x and y. What else must be true? Well, we also it has to be a point on the original function, right? So xy squared plus 3x squared minus x squared y equals 5. These also both have to be true. Now that gives you a system of two variables and two equations, and it would appear, first glance, no, maybe we can do it. So this is going to be messy, but we need to try to solve this system of equations. So I think maybe I can solve this one for x. If I do 2xy minus 6x equals y squared, factor the x out, and then do x is equal to y squared over 2y minus 6. And then plug that in here. So in place everywhere where I see an x, I'm going to write y squared over 2y minus 6 times y squared plus 3 times y squared over 2y minus 6 squared minus, I probably would have done better to do some simplifying there, factor out the x squared or something, but oh well. Y squared over 2y minus 6 squared times y equals 5. Now that's a pretty horrendous looking equation, but remember, it's an equation in one variable. If you're very, very careful, you can find the solution to that by plugging it in to your calculator. And that will tell you the y values for places where we have horizontal tangents on this curve. How do you find the x values? Come right back to here. Right? I made up, I'm sorry that one turned out to be that was a little hairier than I might have wanted for an example. But let me recap by saying once you find one of these, you can find horizontal tangents by setting the top equal to 0. And what would force a vertical tangent? That's right. The bottom being equal to 0 would give you a vertical tangent line, right? So you can find those conditions that way. All right, so that's it. It's really very, very similar to related rates, and shouldn't be too much of a problem there. The difference being that we go through and solve for dy dx now, and we end up with a derivative that's defined in terms of x's and y's. Typically, maybe it's only with y's in it. Maybe it's only with x's, but it's most of the time we're going to get one with x's and y's when we use this technique. All right, we'll do some problems in class tomorrow.